Dear students, today we shall talk about interference due to thin films. In a previous video, I have told you that whenever an interference takes place on account of reflection from two layers of a film, it is actually that the intensity of light is getting distributed. And since the intensity of light is directly proportional to the amplitude square, we say that this type of interference is due to division of amplitude, right? Now, films can be of many types, of many shapes. They can be thin, straight films, parallel films. They can be wedge-shaped films. So we shall be discussing each one of them one by one. But in today's lecture, we shall try to cover up the interference due to parallel thin films, right? Now let's consider one such film. This is the incident ray. A part of it gets reflected, a part of it gets refracted, a part of it gets transmitted. From this point, again, a part of this ray gets reflected, a part gets transmitted, and a part gets reflected again. Then from this point, a part gets reflected, another part gets transmitted, another part gets reflected, and so on. Here it gets transmitted, here it gets transmitted, and so on. So we have a set of rays that are reflected, and this is called reflected system. And we have a set of rays that are transmitted, and this is called transmitted system. So we have to analytically describe two systems, the reflected system and the transmitted system. So let's do that one by one. Again, consider a thin film. Let us first choose to do it analytically for reflected system only. So this is the incident ray, this is the reflected ray, this is the refracted ray. A part of it is transmitted. Let's forget about that at the moment. Then at this point, it's again reflected, it's again transmitted, right? So we have a set of reflected rays. Since these rays are originating from a single common source, we say that these are coherent and they will produce an interference pattern, right? Now let's try to draw the normals wherever they are required. So this is the normal here, this is the normal here, right? And so on. Now, what is the path difference? We are basically interested in the path difference. The path difference is, as always, we drop a perpendicular from one ray to another. The extra distance covered is this much, right? So let us try to name these points also. This is A, this is B, this is C, this is D, suppose this is E, this point, right? So this is angle of incidence here, right? This is also angle of incidence. Now this is angle of refraction. This is also angle of refraction, right? Now what is the extra path length that these rays have covered? It is actually, it can be divided into two. One is the what is the path covered by the ray in one medium and path covered by the ray in another medium. So the extra path covered is actually CADB. So the path difference is basically AD plus BD minus this AC, right? Because AD and BD are identical, they form the part of an isosceles triangle. We can write it is twice AD minus BC, which is the path difference PD, right? But because we know that these two media belong to two different materials, say one is glass, another is air, it has a different refractive index and it has a different refractive index. Suppose the thickness of the film is T, right? And its refractive index is N. So actually we can write for this path difference that it is twice N times AD minus BC, right? Rather AC, I mean to say it is AC AC. Since AC is the path covered by the ray in air, so the refractive index there, mu is equal to 1. So we don't write it. Here it has certain value n, so we multiply it by that. I hope all of you are also aware about a concept called geometric path and optical path. And optical path. See, in a medium, the actual path length covered by a ray is called its geometric path. But when we multiply that geometric path with the refractive index mu or n, we get the optical path. So, optical path is equal to geometric path into the refractive index mu. Remember that in a given time, in a given value of time, a ray of light covers equal optical path in different mediums, right? It is for the reason of differentiating between this geometric and optical path that we have also multiplied the path covered by the ray in this glass medium by n. In the air, we have also done it basically, but because since the refractive index here is 1, so we write it directly as AC only, right? If you have understood this much, then we can proceed. Now, let us see what is the path difference essentially. I have told you that it is twice NAD minus BC. Now, let us turn to the next page. Now, let's try to calculate that, in fact, right? So, how do we do that? So, we have to find 2 times AD and we have to find this AC, right? Now, let us find the sine of angle of I. So, sine of I is equal to AC by this AB. So this AC is AB sine I, right? For this AB, you can write it is AE plus EB. AE plus EB sine of I. Since this AE and EB are same, so we can write it is twice AE sine I, right? Now let's try to find this AE. You can find this AE from this right angle triangle. If T is the thickness, that is the value of DE is equal to T. Therefore, you can find that this AE is actually T times tan of R. Therefore, this AC is actually equal to this twice T tan of R and this sine I. So, this will be first expression, right? Now, you are also interested in finding this AD. AD, what will be that? AD will be given by the cos of certain angle, cos of R. AD is involved in the cos of R. Base by hypotenuse, that is T by AD. So you can write T by AD is equal to cos of R. So AD is basically T by cos of R. So you are done with whatever was required. What was required was this, that path difference is twice AD minus AC, and you have found that. So it is equal to path difference is equal to twice n times what is AD, that is T by cos R, minus AC, you have found that is 2T tan R sine I, right? So that is 2NT by cos R minus 2T. For tan R, you can write sine R by cos R, right? And for sine I, you can write, since Snell's law is sine I by sine R is equal to n, refractive index. For sine I, you can write it is n sine R. So you can write it is n sine R, right? So you can take this 2nt and cos R common. So it is 2 nt by cos r, it is common. So 1 minus this is sine square r, and 1 minus sine square r is cos square r. That cos square r, one of the cos r cancels with this, you are left with 2nt cos r only, right? We are done with the major part of this. Now let us move to the next page. So the path difference between the two rays of light comes out to be how much? 2nt cos r. Now let's go back to the original page again, right? We know that we are talking about the reflected system, and already in a previous video I have told you that on account of Stokes relations, on account of phase change in reflection, there is an additional path difference introduced in the system, right? A phase change of pi, or a path difference of lambda by 2. We shall be adding that here. So 2nt cos r plus lambda by 2 shall be the net path difference, right? And why did we introduce this lambda by 2 factor here? This is on account of reflection, and we know that due to a phase change in reflection, an additional path difference is introduced, and that is given by lambda by 2. Now we shall be equating this path difference to the conditions of constructive and destructive interference. For constructive interference, we know it is equal to n lambda. Now we will not write n here because we have already used that for refractive index. Let us write m lambda. Therefore 2nt cos r is equal to m minus half, right, lambda, or this is 2m minus 1 lambda by 2. So this is the condition for constructive interference, right? For destructive interference, it is again 2nt cos r plus lambda by 2 is equal to 2m minus 1 lambda by 2, right? So this is 2nt cos r is equal to 2m minus 1 lambda by 2 minus lambda by 2. So that is m lambda minus lambda by 2 and lambda by 2, that is only lambda. So that is equal to m minus 1 lambda. Since this m is also an integer, it doesn't matter if we write m for m minus 1. So it is m lambda. So this is the condition for destructive interference. Remember, this is the condition for constructive interference, in which we are going to get the bright spots. And this is the condition for destructive interference, wherein we are going to get dark spots. So this is the analytic treatment of the system which has undergone transmission. Reflected rays. For reflected rays, this is the analytical treatment. Now for the transmitted rays, again, for example, if we remake the diagram, so this was the incident ray, this is the reflected ray, this is the transmitted ray, again it is reflected, again it is transmitted here, again it is reflected, again it is transmitted, again it is reflected, and so on, right? Now for the transmitting system, again we can find the path difference through a same scheme of derivation that we did before. And what did we get in the end? We got this set of equations, 2nt cos r plus lambda by 2 is equal to this much. But in case of these transmitted systems, remember that there is no reflection involved. There is no reflection involved. So there will not be an additional phase difference introduced. Therefore, we will have to put this factor directly equal to m lambda for constructive interference, and this factor directly equal to 2m minus 1 lambda by 2 for destructive interference, right? So in case of transmitted system, the scheme of derivation is again going to be the same, and the path difference between two transmitted rays will be the same thing, that is 2nt cos r. But this time we are not going to add a factor of lambda by 2 because no reflection is involved in case of transmitted rays. So we will put this factor directly equal to m lambda for constructive interference and put this factor equal to 2m minus 1 lambda by 2 for destructive interference. This will give us bright spots and this will give us dark spots. Therefore, the condition that leads to bright spots in reflected system is the condition that leads to dark spots in the transmitted system. That is why we say that the reflected and transmitted systems are actually complementary to each other. And that's all about the scheme of derivation, the analytic treatment of interference due to a thin, straight, parallel film. I hope that gives you a fair idea of the topic.